And we can, the second one is we can convert our third equation to the blue one. Okay? I hope we agree with that. Those are only two things I taught in the first class. So you can see the result, and also you can get the result. The blue one is this one equals to Q, right? And also the fourth class, number 4, equation number 4, can give us a result that if you have the magnetic flux density field, you take the cross-surface integration equals to 0. Okay? Those are the only thing I want to tell you, which is they are Gauss's law. This is a result I copied from the wiki. So the equation from wiki, if you know the E field, you take the cross integration of the surface, you will know how many charges are in this area. This is Gauss's law. You should already heard this before, Gauss's law. Okay? For the third one and the fourth one, number 3 and number 4. Also, we do very similar thing for the first one and the second one, because we are running out of time. I try to hurry up, so please just check the PowerPoint later. Okay, you can do very similar thing for the first one, the first equation, and the second equation. This time you apply this. This is the Stokes theorem. You can also find this equation in your appendix. Okay? If you apply this one, you can obtain these two equations. So, for the first equation, you will see if you have the electric field, you make a line integration, you take a line integral. If the line becomes a closed loop, you take an integration. The answer will become also the B. You have the surface integration, and this result, you take the partial to time. Take the partial to time, and there's a minus sign and minus something. This one is fictitious. This is non-existent. This doesn't exist. Okay, and also you can get a result if you have the second question. You apply this equation, you will have a result. If you have your H field, magnetic field, you take a loop line integral of the magnetic field will equal something. Maybe we should neglect this one. Will equal, this is the current density integral by the surface, the area. So this term is current. For the second equation, you apply this. You will obtain something you should be familiar. This is Ampere's law. You take the line integral to the B field, you obtain your current. This is Ampere's law. Most of you should already know it. I omit one part because that is a part related time varying E field. I just neglect it. I just don't see it for this term. For this term, I don't see it. We just don't discuss it. Okay? We talk about only this term and this term. And this is Ampere's law. Okay? You take a loop line integral, you will obtain the current. This is your second equation. They are the same. This is Ampere's law. Okay? Also, you do the same thing to the E field. You take an integration, a line integration of the E field here. You will obtain the answer will become the change of the H field. If there is a magnet, you change the magnet will become your E field here, so you will obtain the voltage. This is Faraday's law. Okay? So, the first one is about Faraday's law. The second one is Ampere's law. These two are Gauss's law. Those are the rules we are familiar with. Those Maxwell equations, these four equations are not special. We knew this long time ago. Okay? Faraday's law, Ampere's law, Gauss's law. But they are in the different form. Okay? Okay, so that's it. So I make a conclusion here. You can see that this is the result. And you can see I apply these two vector identity. I change this differential form to this integral form. This is the integral form. All of them are integrals. If they are integral forms, you already knew it. You know what happened there. Those are the integrals. Alright? Same thing. Same thing. So, when you ask me why do I have this is epsilon, I say no, this is a capital E, different form, this is also E field. You can change that back to this form. This is an easy one. You don't consider, you say time. You consider time, you write down that in this form. Okay? The notations are according to your textbook. We are still in the chapter 1.2. If you have any question, you can, most of you have a textbook, you can check chapter 1.2. Those are the things I'm discussing. Okay? But I have more details. I tell you something you should know. You should know. This is chapter 1.2. And you change this form by this form. One of the students asked me why this is the partial derivative with respect to time, right? Why here it is j omega, right? Now I'm trying to answer you. there is a function, I call that if what is the difference between these two? Actually, the difference between, I just give you a conclusion, okay? Maybe we need more derivation. The E field, we are talking about, this is related to time, will equals to the E field, not related to time, just only times exponential J omega t. That's it. We call this time harmonic. What is this? This is, as I already write down, cosine omega t plus J sine omega t. Did you guys know this before? This is the Euler's rule, right? For the complex variables. If this is a real and this is the image for a complex variable, you have something here, we call this A. You can describe this complex number as A equals to the absolute value of A, and also this is a phasor form. This is a phase, right? So there is a theta, and that is how the magnitude, angle, and the magnitude. You can define where A is. Okay. This is one of the thing we define where we can find A. We can also have another way to define what is this. We use the rectangular coordinate. For the real part, the axis of a real part, it is cosine theta times A, and for imaginary part is okay, and this is the same. You can see that like the theta when we talk about the theta, because it is a complex variable. Ned, are you okay with that? You familiar? Because they took my class for last semester. We have this information. You already knew this, right? No? But you are fine with that? Okay. The complex. This is a complex number. If you want to discuss with the time, you just times. You just try to multiply your E field to this term. Okay, this is the difference. Okay, and what is exponential J omega t? Because we don't have any time variables inside this function, so we do the partial operators on it. Nothing happened here. Only this part we have t, right? So if we try to derive this term will equals to J omega exponential J omega t, which is, we can also think like if there is a partial operator of t will equal to J omega. That's why I write down this one, and this is why this form can directly become this form. Okay? J omega means the partial differential with respect to time. That's it. This is just a transformation to this one. Okay, now it is important to remember these 4 equations. We will use these 4 equations for whole semester again. So, see this, the star mark. These 4 equations are really important. Please remember it. Okay. And you will derive a lot of theories according to these 4 equations, and this is why we spend some time to explain these 4 equations. If you have further questions about the Maxwell equation, please check your chapter 1.2. Okay? If you have a textbook, it's good for you to review what I'm talking about. We are also taking a video. You can check the website. I will update the website. And you are welcome to ask me questions after class or maybe somewhere else, okay? Or in the lab. Okay? So I finished the first thing I tried to discuss. Then we are in the second topic. We are talking about discuss the boundary condition. This is the second topic. The boundary condition is maybe chapter 1.3, right? Materials and boundary conditions. But I will try to discuss about more materials later. I will try to just discuss the boundary conditions and make it easier. So what is boundary conditions? For the 4 Maxwell equations, you can see the relationship between E and H, right? Again and again. But what happened? As I asked you, if there is an E field in the air, if there is an E field in the maybe Teflon, FR4, or some different materials, they have different equations for the this is the materials, right? We already know this one. The boundary condition is the way we try to discuss what happened if boundary condition means what happened if there are two materials. We call this media 1 and media 2. And there is a field E and H. For this E, I call this one this is 1, this is 2. This is E2, E1, H1, H2, right? But different material, I just applied different epsilon, different mu. So that's easy. But what happened here? What happened on the boundary? You say, in here, you can apply epsilon 2, mu 2 for your field. But for here, you have different media. What happened on the boundary? Is there any theory talking about this boundary, about an E and H field? This is boundary condition. The Maxwell equations must be true everywhere. Must be true. So, what can happen here? So, let's see the result of the boundary conditions. We already discussed this, right? B equals to mu H and D equals to epsilon E on the board, okay? So this is about what is the material. And what happened on the boundary? They try to make not regular boundary, not just only a line. We need to calculate result for all the answers. So we make, because we already know the knowledge of the vectors, we can write it, we can have an equation for all the conditions. The more the better, the general cases. Okay, for us 1, 2, 3, 4, 4 equations. We apply, as I say, they are important, right? You see this again and again, Maxwell equations. We apply this on here. So what happened to the field on this boundary? What happened to the E field and what happened to the H field of the boundary? First, we apply this equation. Okay, time to have your extra point. 2 points. What is this equation? Tell me. Easy. Quick.
Gauss law.
Yeah, Gauss's law. Good. You should quick. Those are just easy way to earn your points. You don't need to study hard for a midterm. Okay, I will show you your result later after the class. Gauss's law, right? So what is Gauss's law? If there is a surface integration about something in the air, right, or in the media, if there is a close integration, the result will equals to Q. How many charges are in this surface, right? So what we are going to do is we make a surface integration on the boundary, on this boundary, okay? But we try to make this area very special. How special? If the surface on the top side, you need to think in this in 3D dimension, okay? You integrate this surface because we want to integrate in 3D. So how do we do this? We integrate this, the face surface, and another face surface on the bottom for the first media. This is the media 1 and this is the media 2. We make this area, the bottom surface is in the first medium. The top surface is on the top in the second medium, okay? And we also make the height of this cylindrical is very small, h. We make this very small. Do you know cylindrical, right? This shape. This is there's a circle, but they have a volume. Cylindrical, right? This is just a volume. Okay, you have a circle up in the bottom, and a circle in the bottom, and a circle in the top. And the height of this area H is 0. So you will have only 2 surfaces on the bottom, on the bottom and on the top. For the bottom and the top, only 2 surfaces, and then you apply your Gauss's law on it, and then you can obtain this result for the third equation. There are 2 equations for Gauss's law, right? The third one and the fourth one. The thing is, you need to define. I think there are more details about you really how to calculate. You make the surface, the closed surface integration. You need the D, the vector D dot your vector of surface. Okay, there are more details. I assume you don't have the experience to do this calculation, but it's fine. The result is just the direction of surface is, if I have a surface, the direction is the direction of the direction perpendicular to this surface. Okay? If I have S here, and the direction of this surface is to this direction, and we call this N. If this is the normal, the unit vector of the surface N, when you make the surface integral, this one will equals to this surface, because the height is 0, right? So the result will become this surface dot the direction of something perpendicular to this surface minus the surface dot the different direction of this surface, because the surface on the top is to the upside, and the direction of the surface in the bottom is to a different way. So after all, you will obtain that d2 minus d1 dot n will equals to Q divided by surface, the area, which is rho s. This is a current density. Raise your hand if you understand. If you now, I will tell you again. Okay? You good? Anyone? Okay. Do you want to explain to students? If you can do that, I will give you 5 extra points. Anyone? You want to explain in Chinese? I give you 5 extra points. Okay? Speak louder and stand up and tell people what I'm talking about the first boundary condition. Okay.
Just tell people. Oh, I'm sorry. I try to make him speak in Chinese to other students, but if you don't understand, maybe I will explain to you. Okay? Yeah, 5 points if you explain well.
对整个体积积分的话，会等于对每个面积分的总和是一样的。然后
This is Gauss's
我
law.
们让那个 h 进入是圆，那要代表那个圆柱形旁边的体积就是直接忽略，只剩上面跟下面的圆形的圆形的面积。啊，这样子，那两个面的面积，就是那两个面算出来的带电量，它们的差值一定是那个圆柱体里面的带电量，就是一个进去一个出去嘛。那里面有多少带电量？那进去跟出去两个差一定是里面那个电量。
Close, but not very perfect, but it's close. I think you already make people understand more, right?
Okay. I will repeat what he is talking about in English. Okay. What is Gauss's law? Gauss's law means if you try to integrate all the area, the surface area, with if you know the D or you know the B of the field, D or B, you integrate all the surface. It must be closed surface. You integrate that. The result is equal to Q. This is Gauss's law, as we already discussed. Okay? But if this area is spatial, our area is cylindrical with the height close to 0, you will have the result only has 2 surfaces on the top and on the bottom, okay? Which they have different direction. because the definition of the surface, the definition of the direction of the surface is somewhere to the upside to this surface. So for the top of this surface, the direction is here. For the bottom of this surface is to down, is to another direction. They are opposite, different direction. So this is a D field on the top, another D field in the bottom. You must object. You need to use the D2 minus D1 because the direction is totally different. It's opposite. Opposite means 相反, negative, positive and negative. So two different positions. So that's why we have D2 minus D1. Okay? Then the result of this one will equals to, because this is the integration of the surface, which means you multiply the result to the surface, multiply to the surface. You can get, this is delta S, and you multiply to delta S, which means equals to Q. You can move the delta S to here to Q. So you know Q delta S equals to Q over the area. So this is another notation. This is the charge surface density. Okay? Okay? Okay, so what do we obtain? After all, what is the result? The result is, on this boundary, if there are two materials, D2 minus D1 equals to this one. And then you need to, if this is normal, the normal direction of your D field on the top and the normal direction of the D field in the bottom, the difference between these two D fields will equals to ρS, which is charge density. Okay. So you obtain the relationship of your D field, which is related to your E field, according to different material. Okay? So you know what happened on this boundary for a D field. Okay? Question? No? Well, we will use this later also, especially for waveguide. Or maybe, or not, if we will discuss the wave, go to different material. This one we will apply this one. Okay. If you have some material, there are two different material, you will know D2, maybe this D1 and the D2. They are the same if there is no source. This is a source. This is source, right? Usually, I will tell you that there is no Q. There is no source, which means the direction perpendicular to the surface, two E fields, the two D fields are the same. If there is no source, what can we obtain? There is a field and the media 1, media 2. I have some D1 and a D2. If there is no source, which means D1 equals to D2. If the field is the same direction, which means epsilon 1 E1 equals to epsilon 2 E2. We know the relationship between these two fields on the boundary. This is how we apply the boundary condition. What happened on the boundary? Okay, and the Maxwell equation is still valid. You can still use Maxwell equation. Everything is still perfect. Okay, so you can obtain epsilon E1 equals to epsilon 2 E2 if the direction of D1 and D2 are the same. Any question? According to this result, maybe we can have some calculation. Okay, more questions. Time to earn your points, okay? If you don't earn any points, which means you don't show up in this class, you don't have any point, okay? Question. Raise your hand. This is five points. 5 points. Can you just let people have some opportunity to earn more points, please? Okay? If nobody want to answer, maybe you guys can. If you already have an opportunity to earn your point. There are two fields. And this is the boundary. Okay? 2 for 2, but media. Okay? And if there is air, call epsilon 0. If this is, okay, you guys like FR4, epsilon R equals to, just use 4. Okay? Just use 4. It's easy to calculate. Okay? If your E field in the air is E. So what is the E field? This is 1, 2 equals to. Anyone? Raise your hand. 5 points. What's the answer? I have the field in this area. I have another FR4 material. What are the E field inside this FR4? What? Raise your hand. If nobody answer, maybe you want to answer. Just, okay, you can write down the answer. What is the E2? And the E is the direction to normal to this area, this plane, this surface, okay? It's okay. Anyone? Okay, nobody answer. Give me the answer. You want to say it or just write on it? Okay. I said 5 points, right? Okay. Good job. So what is the answer of the E2? You need to make the equation, not to write down the result. You want to give me a result? Is this a result? Is this a result? Close, but I will give you some break point. Well, I'll give you 2 break points, but the answer, you need to think about it. Now, what's the answer? Show me the answer. 5 points. What is E2? Is that answer? Oh, maybe I missed something. Okay. Wait. For this material is air, okay? So epsilon 1 equals to epsilon 0. Okay? For this material it is FR4. So epsilon 2 equals to epsilon 0 times 4. Do you want to revise your answer? So this is 4 times epsilon 0 for this material. So what is E2? E2 is yeah, you got 5 points. This is the answer. Because you want to make this equation. So this is what this is for. Okay? For most of the time you don't have Q. You don't have Q, so it just equals to 0. But if you have a charge on the boundary, you need to consider the charge. 5 points. Whoa, you got 9. Okay. So this is a boundary condition, number 1, number 2. Also, you have 2 boundary conditions for this case. We apply the result for we apply the first and the second Maxwell equations. Very similarly, but in this example, maybe we can use the Ampere's law. For you, it's easy to understand Ampere's law. You loop integral to a H field, U are equals to the E field, the changing of E field, because it's J omega, changing with time. If this is not changing with time, it's equals to just only J, is current. So we apply that to this one, and similarly, we can get a result. If you have the loop integral of the H, because they are in different direction in the top, on the top or on the bottom, so they are different, and you can see that this is the H field to this direction, not the normal direction. It's a direction, I don't know how to say that. Ned, do you know how to say that? In this direction. This is normal direction, right? This is a transient, right? The cut the direction in this way. Horizontal is talking about sometimes vertical and horizontal. Yeah, but you are basically right. But there is, I think there are some more formal way to say transient direction. 切面的方向。The normal 垂直。This is normal direction and transient direction, I guess. Okay, so you apply these 2 equations, you will obtain that the transient direction of E field will equals to the direction, the result of MS. This doesn't exist, right? But this exists. This is a J. This is the current density. And you will see that there is a vector close something. So, which means the direction will change. If you have a direction by this way, in this way, and then you have a loop direction. I will define that like this way. N is direction of this direction, right? Normal direction, close to this H. H is go to that direction. So you will have your result, use your hand. N cross your H. H is this direction will equals to your final N cross H will equals to the J direction. And if the direction is to this way, close to H. Let's try again. If you define your E is go to this direction, and close to N, you will have the N. The result of N is outside the paper. You can see the small circle here. Okay? And if your direction N is this direction, close to the H, this direction, so your J direction is inside the paper. This is more complicated than the Gauss's law because the direction is changed. You need to consider different direction. But if you don't consider the direction, you want to know the magnitude only, it's very similar. They just minus each other equals to maybe 0 or maybe equals to something related to J. And this one will times 2. Yeah, the J is J divided by dl. How long it is? It's line density. This is the current density. Okay. So here we obtain the 4 equations. We finally obtain four equations. I think we need to have some time to answer the first question, right? Do you see the first question? I think we don't. I haven't get to the second question, but you need to answer the first question. When we derive these 4 equations, the boundary conditions from the Maxwell equations, those are the result we obtain. And that is an example. There was an example. You can practice the result of the boundary conditions. Okay, I will give you more time. Just let me finish the boundary condition, okay? So for these first 2 equations, you obtain from Gauss's law. You know the normal direction, the relationship of the normal direction of the E field and H field, the normal one. And for these 2 equations, you will know the tangent relationship on the boundary for the E field and H field related to also the sources. If there are no sources, the same as our example, if there are no sources, you can just say that D2 equals to D1, D2 equals to D1 in the normal direction. And the E2 equals to E1 and the H2 equals to H1 for the tangent direction, okay? If there is no source. There are 2 different cases as shown in the textbook. If there is a perfect conductor we call the electric wall, which means there is no magnetic source. Then you have only the current source. You will make the third equation equals to 1 only, and also obey these two equations. If there is a perfect conductor. If there is a magnetic wall boundary condition, which means you have only magnetic source. Actually, this is, as we said, this is a fixtures, magnetic source only, but there is no current source. So the first and the fourth equations are both 0. We have that. The third equation not 0. Okay, so this is a conclusion of our result for the boundary condition. And we finish the second topic I'm trying to teach you. And I think we don't have enough time to finish the third topic, the wave equations. Take some time to have a break. I will tell you how to answer the question, okay? We will just take a break.